Okay. So this is going to just kind of be going through the rest of Unit 6 is the goal. So it might be a bit long, but feel free to take this at your own pace, multiple sittings, whatever. So mostly what we've been talking about so far is talking about energy changes from like heat transfer, so just from things being in contact, or we've talked about physical processes so far, um, like phase changes or dissolving stuff. But from here on out, the big focus is going to be on chemical reactions. Mhm. So we've already kind of talked about this, but let's make sure we're all super clear. Because to understand how much energy comes from a chemical reaction, we have to understand that that's actually from the forming and breaking of chemical bonds. So just to recap, if we break a chemical bond, that always requires energy. Because when we break a bond, we are taking it from this stable form where it has bonds. They all have full shells, they're chilling, they're happy, and we're forcing them out of that. So that always requires us to put in energy. Versus if I form a chemical bond, I am making something more stable. Therefore, I get to release energy. It's all about that stability. And so whether we have an endo or exothermic reaction is really about the balance between these two processes. If I end up getting more energy from breaking bonds, or there's a bigger input of energy needed for the breaking of bonds than I get back out when I make the bonds, then overall I end up with an endothermic thing because this requires that we absorb energy that is not absorbed. This gets us a release of energy. So we have this balance of a negative change and a positive change. So if we have more breaking, that means that this has an overall positive delta H. Okay. Exothermic processes is opposite. It means that in this balance of having to absorb some energy and then getting to release some energy, we are doing more of the forming, more release of energy, which means that overall our net change is a negative delta H. Okay. So that is what we really mean when we're talking about the enthalpy of a reaction, the delta H of a reaction. It is the net change in energy, in enthalpy from a chemical reaction. Did want to clarify a thing about units. When we are reporting our delta H of a reaction, the proper units should usually be kilojoules per mole. And so like, it's pretty much always kilojoules per mole. Like maybe you'll see joules per mole, but just keep track of it, whatever it is. But the thing about this, I wanted to clarify. When we say that there is a enthalpy of reaction of a certain amount of kilojoules per mole, The per mole part, we're referring to the moles of the reaction. Moles of the reaction. So it's about how many times the reaction happens. So you got to be careful about your stoichiometry about those ratios. If it gives you, if it's asking about a certain reactant or a certain product, make sure that you check that ratio. What is the ratio of how many of those I get versus how many times my reaction happens? So something to keep in mind, moles of reaction, not moles of just one thing. So one thing just to point out, I wanted to mention, uh, one type of reaction that is always exothermic are our combustion reactions, which perhaps doesn't feel that weird to you. I mean, it's why we use it to like make energy and stuff, right? Also maybe you've seen these reactions written out as like organic stuff plus oxygen plus CO2 plus water plus energy. If you've ever seen them write energy or heat as a react or sorry, as a product, indicating that we produce heat, like that's what they're representing there. So just to point that out. So let's see a kind of problem we might be asked about. So we are given a reaction, and off to the side, they report our enthalpy of reaction, and we get a number for it. And it is asking for the change in heat. So the change in heat, just to clarify the words that they're kind of cueing you into. If we're asking about heat generated by something or heat from a change, that's going to be a Q from the combustion of this many grams of ethanol. And just to clarify, this is ethanol. Okay, so we can figure this out. There's multiple strategies. You might remember, here, I'll just write it off to the side. You might remember this guy. Sorry, nope, N. Wish it was M. You might remember that. So one option is to calculate your moles of reaction and then plug it in here. So that's one option. Or we can do a stoichiometry. Stoichiometry fan, so I'm probably going to try it this way, but if you prefer, we could do it in 2 steps if you want. So to get my heat, which is going to be whenever you solve for Q, whenever you solve for heat, it's always going to be joules or kilojoules. So I know that I'm going to be trying to solve for my kilojoules here. So puts the thing I know with kilojoules. Let's start with that. Good place to start. So it gave me my enthalpy of the reaction was negative 1367 kilojoules per mole of reaction. Okay. And I want to relate that back to the amount of ethanol I have. So just to kind of show that little conversion, every time this reaction happens, it requires 1 ethanol. So the ratio here is 1 mole of reaction to 1 mole of your ethanol. But if it wasn't 1 to 1, this would be something that you'd have to account for. The lazy chemist way of writing ethanol. And I was given grams, so I'm going to want to make my moles into grams in order to cancel that out. And they gave me the molar mass. And they gave me a starting amount of ethanol. So totally, I mean, like any stoichiometry, you could have started with your grams and then worked it the other opposite way, whichever you prefer. So there we go. All my units cancel out. I'm solving for kilojoules and multiply that all across, divide out. I would get that I have a negative 445 kilojoules released from this reaction. It was quite a lot, TBH. I did just Google this, and this is the enthalpy of reaction it gave me. So who's to say? Maybe there's some flaw in this, but you see the process. Um, da, da, da. Yes. Okay. So that is the change in heat is a negative 445 kilojoules, indicating that this is an exothermic thing, exactly what I would expect for a combustion reaction. Did want to point out a little like wording thing, a little phrasing thing. If this question instead asked for the amount of heat produced, or if you were ever given a word problem where they say this amount of heat was produced, that implies that it was exothermic. It implies the negative. So if it was a word problem and you need to plug it in somewhere, make sure you're plugging in a negative of that value. Or if it was like a multiple choice question and it said like how much heat was produced, you wouldn't want to pick a negative thing because it's producing a certain amount. It's an implied negative. So we could also report this number as 445 kilojoules released. Okay. So just to clarify, a little tricky thing that could come up. Alrighty. So far we've kind of practiced with constant pressure calorimetry, coffee cup calorimetry, where you just have like a container and there's water and you put something in the water and you measure the temperature change. This is the other type of calorimeter. It's called a bomb calorimeter. It's not as cool as it sounds, or like, it's still cool, but there's like a container that has like um has oxygen, air in it. So a little container, but is, well insulated enough that we're assuming that any reaction in there, if it produces energy or consumes energy, it'll go into the water that surrounds that little chamber. And then it's super insulated around the water. So this is how they actually do testing the energy from a combustion reaction. Something that needs fire would be difficult to do in water, right? If you've taken honors chem and we did like the janky version of this, where just like we burned a Cheeto underneath the thing, you know, if you know, you know. Same concept, but this is like the much better version of it. But just so you know, another strategy, but same concept of other calorimetry. All of the heat transfer from the reaction happening in here goes into the water surrounding it. So, like any calorimeter, we know that the net energy change of the universe must be equal to any heat transfer that happens here. So we know that there is going to be some heat from the reaction, and we know there's going to be some heat transferred with the water. So we know we could set these equal and opposite to each other. Surroundings and system, equal and opposite. Sorry, I should have like read the question with you before I just started yapping, but it's saying that we have 50 grams of water in the chamber, so 50 grams of water, and we are putting 15 grams of ethanol in here. So we're combusting the ethanol, and we want to figure out how much the water's temperature is going to rise. And just to clarify the phrasing here, temperature rise, implying a change, temperature rise. So we are trying to solve for our delta T. They didn't give you an initial temp, but you don't need it. We're just saying the difference. Okay. So if we were starting from here, we'd have to calculate our Q of reaction and like all the stuff, but we already have it from up here. So we already know that this reaction, here, I'll write it just so we see the process. If you were starting from the scratch, you would do something like this. And then let's plug in what we know. So we already know that the reaction releases this much heat. And we know that we have 50.0 grams of water. And it gave us the heat capacity of water as this. And then what we don't know is our delta T. So I'm going to leave that. Okay. Now something, there's a lot of changing units in this unit. So be careful. Maybe you noticed already, we have a kilojoule over here, a joule over here. So at some point in this process, hopefully you'd notice because you wrote your units in your equation that these do not match. So at some point we're going to need to fix that. I'm just going to choose to do it now. You could have done it before you plugged them in. We could choose to change either one of these guys. I'm going to choose to change this one to joules. So I'll just show the process in case we forget. There are 1 kilojoule per 1,000 joules. Multiply it by 1,000. So really what we're solving is, I'm going to change this. Really, it's that equal to, I'm not going to rewrite all that stuff. Okay, so a little bit of algebra. Can we solve for our delta t? So, practice, make sure you can do it. But our delta t, at least what I got, was this, which is a lot of degrees Celsius. But it's only 50 grams of water. I don't know. Interesting. So yeah, that's the process. So another application of calorimetry. This is actually how we this is pretty much the setup of like how we know how many calories are in like food is we use bomb calorimeters. So like light them up or light up their ingredients in here. And that's how we figure it out. Cool. Okay, so this like for the rest of this unit, like I mentioned, it's all about the enthalpy of a reaction, the enthalpy change from a chemical reaction. So there are a lot of different strategies we can use to figure out our enthalpy of reaction. One of them is kind of what we just saw. So being able to see the temperature change of the water, being able to figure out how much heat the water absorbed using this concept to then figure out how much our reaction released. That's one concept. So that's one way we could do an experiment. But there's also ways we can do it with some math tricks, and they're not too bad, don't worry. First one is called bond enthalpies. So like we've talked about before, the change in energy, the change in enthalpy, our net change of a reaction is determined by the balance between the energy required to break bonds, which would be a positive enthalpy, versus the enthalpy from forming bonds. So the heat absorbed versus our heat released, what is that balance? So if that is like what determines our delta H, you can actually solve for delta H using something based on, if you had like a list of the energy of each of those bonds, you can use it to solve. Okay, so this is the fancy chemistry word for that is a bond enthalpy. So that's the energy stored in a chemical bond. So any bond can have a bond enthalpy, and then depending on what we're doing with that bond, if we have to break it, then we're going to have to absorb, or sorry, if we have to break it, then that bond will absorb energy equal to its bond enthalpy. AKA it's going to be a positive change. But if we get to form that bond, we're going to release energy equal to its bond enthalpy, a negative change. Okay. So I want to show you kind of a visual, kind of breaking down what's going on in our reaction coordinate. It's kind of like an alternate way of drawing it, which I think is kind of helpful for understanding this process. So like, let's say a made up reaction. A2 plus B2 goes to make some AB. So in order for this to happen, I'm going to have to break the bonds in my reactants and then form my product bonds. So the way we can kind of think about this, let's make this energy or enthalpy. And let's say I have my reactants. So I have I have AA, because it's A2, so those two are bound together. And I got B with a B. So in order to proceed, I'm going to need to break A away from A and B away from B. And that is going to take energy. Oh, okay. So in some like intermediate state of this reaction, there's a point where we have these disparate atoms without those bonds anymore. And then they're going to come back and reform. They're going to make new bonds. And that process is going to release energy. Until we have an AB and another AB. So it's really about that balance, two different energy processes. And then what we actually get for our net change is the net change. Here's our net. So, sorry. So here's our net change on this visual, which would be equal to our delta H of reaction, which in this case, we can see it goes up from our reactants versus our products. That's change. So I'm not going to draw the opposite one, but you could imagine if there was a different balance, if it was less breaking, but more forming, we'd end up with a different net change. We'd end up with a exothermic process. So, that ratio. And this also applies well to the dissolution that we talked about back in like 6.1 slash in class. So you could think about this process also with that, those two different steps to the process of dissolving a salt. So something you might want to think about, another good way of understanding the net change. Okay, so if you're using this strategy of just looking at your bonds and how much energy is in the bonds, the way we could utilize this is with this reaction. The net change or change in enthalpy from a reaction is equal to the sum of the bond enthalpies of all the broken bonds plus the sum of the bond enthalpies from all the formed bonds. So basically you can think of this as all of the bonds in your reactants. And this one as all the bonds in your products. Okay. Now, the thing that you got to keep in mind with this guy is that if we are forming bonds, again, all those enthalpies are going to be negative values. Okay, so if you're breaking bonds, you're releasing energy, you have negative values that you're plugging in here. Some people choose to kind of rearrange this because we know that all of these are negative. It could be rewritten as this. So up to you, which one will be easier for you to keep track of. I will say the second one, we have some other reactions that are similar but are the opposite. So you'll see them in a sec, but just be careful. As long as you know that you're keeping track of those negatives properly, you can use either formula. And this one is not on your formula sheet, unfortunately. So pick a strategy that you're going to be able to remember. Broken. I prefer the first one, or you can remember this one. Either way. Um, Cool. So how this works is that we like have done a bunch of experiments and figured out like what is the average enthalpy contained in any given bond. And so for any question like this, you would be given some kind of table like this with a bunch like a list of a bunch of different bonds and their enthalpies, and then you would use it like this. So let's look at an example. And the thing about this is when you are given a reaction for this type of problem, it's about the bonds, how many bonds formed and broke. So you gotta kind of write out your Lewis structures. You can try to do it in your head, but it's so easy to mix up. So just write them out. Save yourself the hassle later. So we have this reaction, and just to represent what this means, we have these different things going on. Oh yeah, and I did want to say that. For these, it's the bond. These are all of the bonds in the products and the reactants in a balanced reaction. So it's the total number of bonds formed, total number of bonds broken. So that 2 there is important. We have 2 of these guys being formed, 2 separate Cl2H bonds. Okay, so let's try our formula here. Try it on your own. You know, this is all just like once you have the formula, you can probably try it and go for it. Formula is delta H of reaction is equal to the sum of the bond enthalpies broken minus the bond enthalpies formed. Okay. So let's look at that. We have 1 HH bond. So I'm going to look back in my table and find the data for that, which would be 400 and something, 432 kilojoules per mole. Looking at my other bond that got broken is the ClCl. So I look up the data for that. And those are all of the bonds broken. And then on my product side, I have formed 2 moles, so 2 separate bonds, 2 separate HCl bonds, which each have a bond enthalpy of negative 332 because we are forming those bonds. Okay, that's what I got. So make sure you can get the same. And then we're given a little graph. So take a second. Can you figure out which one is the correct graph for this? We have an enthalpy change of negative 193. It's okay if the number is slightly different. Don't worry about it. It's because they used a different table of values than me, and I didn't bother using theirs. Whatever. Don't worry about it. But hopefully you're able to identify that is our right graph. Because we have had a negative change in enthalpy, our products have less enthalpy, less energy. Cool. Another one. So again, I'm going to draw out the Lewis structures just so we can clearly tell what bonds we have going on. I have 2 of my oxygens. of two separate O double bond O. I have a CO2, which looks like that. And I have two separate H2Os, each one looking like this. Okay. So, they get complicated. You got to keep track of quite a few little things. But here, I'll just kind of list it out. I feel like that tends to be helpful. We have four C2H bonds. We have two O double bond O bonds. We have two C double bond O bonds. And we have 1, 2, 3, 4 OH bonds. Okay. So I would look back up at my table and be able to calculate this. Delta H of the reaction is equal to the sum of the bond enthalpies broken plus the bond enthalpies formed. All right, so I have four CH bonds that were broken. So looking back up at my table, those would be this much. So practice, make sure you can set it up the same way as me or in a way that works for you. I have two of my O double bond O's. Looking back up at the table, and those are all of my reactants that got broken apart. And then we want to figure out our ones from our products, all the things that were formed. So I had two of my C double bond O's in CO2. So that would be a negative release of enthalpy of this much for two separate bonds. And then I also have four OH bonds. Okay, so plug it all in your calculator. I will say once in a while you get to cancel some stuff out at this point, so look out for that if you want to save yourself a few seconds of plugging in your calculator. But plug it all in. I think you should get this. And always do that logic check. You might recognize this as a combustion reaction. Should be exothermic, and we just checked it out because I see it's a negative. I know it is releasing energy. It is exothermic. All right, so that's one strategy for figuring out our delta H of reaction. And then there's something called enthalpy of formation. Um, delta H subscript F with a circle. So this is the change in enthalpy from a substance forming. And just a note about standard, like what the heck does that mean? I mentioned this a bit earlier, but let's do some more detail on it. When you have that little zero, that we are representing that something is in its standard state. So what does that mean? That means a lot of things. For one, like it should be at 1 atm. it should be at 25 degrees Celsius. If it's a solution, we're talking about a 1 molar solution. We are talking about a pure substance with no contaminants, so only talking about that one substance being formed. Substance. And we are talking about them being in their common form. So we're talking about them being produced, so we are forming so just what I mean by that is like the way it's going to exist most often in nature. So if I'm just talking about if we're talking about our standard formation equations that I'm going to clarify in a sec, we're talking about, like, for example, like oxygen. We all know that that exists in nature as a gas, not as this. That is a form of oxygen, but it's not the normal one. Something you also might want to know is that graphite is the common form of carbon, not diamond. Again, makes sense, right? We don't have many of those. Okay. So a formation equation, what we're talking about is actually creating something from its elemental components. So there are very specific criteria for this. A formation equation is a reaction that forms 1 mole of a substance, of like a compound or of an element or of anything, of any chemical. From elements in their standard state. So if all those things are met, then we are talking about the formation equation of something. So that is actually what we're talking about when we're talking about the enthalpy of formation. We're talking about a reaction like this. How do we form something? What is the heat from that process? So here is like an example. If I'm talking about the formation of iron 2 oxide. So that would be this guy. If I wanted to talk about the enthalpy involved in forming that, I would want to do for 1 mole of it, so 1 mole of it, and then make it from the elements in the standard form. So element I need is iron, and its standard form is just a solid iron. And then I would have to mix that with some oxygen gas, which I know exists as O2 gas. That is its elemental form. And it's a balanced reaction. So the weird thing about these guys is you'll often see fractions because by definition it needs to be for 1 mole of these guys. So it's going to be, this would be the formation reaction for this guy. So then if we knew that, we could report its formation enthalpy as this. Okay. So this isn't like something coming up with these isn't really a skill we deal with in here. I just wanted to show you one so you like know kind of what we're talking about. We're talking about forming something from its elemental components, and then this is what we get from that, the delta H of formation, the enthalpy of formation, standard enthalpy of formation. So when you get a table of these values, that's what we're talking about. We're talking about the energy to create 1 mole of it. Something to note, usually what you're going to get is a big old table of a bunch of these values. So it would say the enthalpy of formation for this is this. So for a compound, we get its enthalpy of formation determined from an experiment or some kind of standardized comparison where we came up with a bunch of these. Usually you'll get a full table. Just wanted to note that if you're forming an element in its standard state, that element's energy of formation is always going to be 0. So, like, you'll notice in tables, like I'm going to show you some, if you had the enthalpy of formation for this is 0, the enthalpy of the formation for this is 0. So their formation is elemental formation is 0. So just so you know, but they'll usually give you that. All right. So how do we use this? Very similar to the last one. And this one is on the equation sheet. We know that the standard enthalpy of reaction is equal to the sum of the enthalpies of formation of our products minus the sum of the enthalpy of formation standard of our reactants. Okay, so that is on our equation sheet. You might notice there's a bunch of them that look the same. Super common setup for us to do reactants minus products, or sorry, very common setup to have these reactions where it's products minus reactants. Just like it's super common for us to do final minus initial when we're talking about change. So just keep that in mind. This one you will get on the equation sheet. So it's just what the just what the equation says. So pretty straightforward. Let's see if we can do one. So we have a reaction and we have a table of this. And it says we have, what is the standard enthalpy change for combusting 2 moles of propene? And propene is this thing. And notice when it says 2 moles of this, that is referring to us doing one of these reactions. So if it said only 1 mole of propene, then we'd have to make adjustments to determine that enthalpy. If it says 2 moles of propene, we're talking about doing the whole reaction once because that ratio is 2 to 1. Okay, let's look at that formula. Standard enthalpy of reaction is equal to the sum of the standard enthalpy of formation of the products minus the sum of the standard enthalpy of formation of the reactants. Okay, so we just take a look-see at the data we were given, and we match it up with the products and the reactants. So let's do our products first. One of the products we made are 6 CO2s, and we get that for each mole of CO2, that is our enthalpy of reaction. So we would do 6 times negative 394, and you plug them in as is. Some are going to be positive, some are going to be negative, just by nature of like what the bonds are in that thing. The other thing we produced is 6 waters. Ooh, cool, cool. So I would look for the enthalpy of the water, which is that. Minus the enthalpies from our reactants. So we have 2 of the propenes, which is 21 kilojoules per mole. And we have 9 of the oxygens, but their formation enthalpy is 0 kilojoules per mole. Because it's an element. Always going to be 0 for the elements. So a little calculator action there. We should get our delta H of reaction as negative 3,858 kilojoules per mole. The delta H of the reaction should be reported per mole. Some people drop it sometimes. I don't think you should do that. I think it should be in kilojoules per mole because that is referring to per mole of reaction. just to clarify. So even though you multiplied them by those coefficients, the moles didn't cancel out. They just you translated it from moles of that thing into moles of the reaction. If you want me to clarify that further, let me know, or you can just assume that your units are going to be kilojoules per mole. Still kilojoules per mole. Okay. Another one. So the standard enthalpy of reaction is equal to the sum of the standard enthalpy of formation of the products minus the sum of the standard enthalpy of formation of the reactants. Whatever. We have numbers. In our reaction, we have information about our products and our reactants. Our product, we got benzene over there, and we know that its formation is, we have one of them, and we are doing 83 kilojoules per mole. Okay. And our reactants, we used 3 of that, each with a reaction, formation energy of this, blah, 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 multiply, and you should get this. So yeah, very repetitive, almost the exact same thing, just with like knowing how to use different numbers for both of the 2 strategies so far. A little tedious, but just keep track of your numbers. Make sure you're clear on what you're plugging in. And yeah, let's take a look-see at the next thing. So our last way of being able to determine our enthalpy is with Hess's law. I don't know why some people don't do the apostrophe S rule correctly with his name. It's just what we do. So in case you were wondering, I don't know why there are 3 S's in a row. It just is what it is. But Hess's law tells us that the enthalpy change of an overall process can be found from the sum of the enthalpy from individual steps. Okay, so here's another vague reaction. So yeah, I wanted to know the enthalpy change for the reaction A becomes C, and I knew some data about other reactions. And this was just me being silly when I was typing this out because I was going to have more steps and then changed it. This is just a typo. How about you go ahead and change that? So let's make our lives easier. Pretend that this says B to C. That's what I meant. So this is, kind of a similar like setup as when we were doing our reaction mechanisms. Similar vibe. We just this concept that just because like I'm forming bonds in one process and then breaking bonds in another, I'm still like forming and breaking the same bonds. So we can use kind of this net change to find our overall reaction. Here, let me show a visual for that to explain it a little bit better. Overall, I'm doing this reaction of A to C, and I have some kind of delta H of reaction for that. So that's one process, breaking all of the bonds involved with whatever A is, forming all of the bonds involved with whatever C is. And, if those were one step, that's fine. But if I had intermediates that were then formed and then broken, like their bond enthalpies and stuff are going to cancel out. So getting to that point, if we took this little detour and did these two separate reactions, we'd still get to the same point. The process can be made up of these different steps, but still have the same net effect, which is why this works. Something called a state function, where like the net how you get there, the journey doesn't matter. It's just the ending states that matters. That's a common concept. Not something we do in this class very much, but it's just the thing. So that's like kind of the why. But knowing how it works, all you gotta do is know how to make a net overall reaction. So we can see that if we canceled out the intermediates, this is our overall reaction. So I could find that the enthalpy of the reaction is actually just the delta H of both added together. Okay, so this is a common thing. You'll get given like a list of a bunch of different reactions, and you're gonna have to figure out how to make those individual steps, those different reactions you got, into the reaction you want. Okay, so identify your overall reaction, and then you're going to mess with the reactions you have so that they will add to your overall. So sometimes they'll give you a reaction and it doesn't, like maybe what you want as a product is a reactant in the reaction they gave you. So you're going to have to flip that whole equation, and you're allowed to do that. So you can flip the reactions, but the only tricky part is that you need to remember, if you flip the reaction, whatever you do to the reaction, you have to do to the enthalpy as well. If you flip it, you need to flip the sign of delta H2 for that step. Or kind of like, I forget when we've done this. I forget when do we multiply the whole reactions by some things before? I don't know. We've done something like this before, I think, but we could also multiply whole reactions by a factor. So like say the whole thing needs to be multiplied by 2. You're allowed to do that. It's as if you had to do the reaction twice in order to get your end result. But if you do that, don't forget to multiply delta H by it too. So super easy to kind of forget about delta H because it's off the side, but that is the most important part. And then you sum it all up, make sure it actually matches your target. You didn't mess anything up. Everything cancels out the way you want. And then you can add up your delta H's. So let's see an example. So here is our overall, our goal. And here are some options that may sum up to our goal. So, it kind of just takes practice getting used to recognizing these. But you'd want to look at your reactions they gave you and try to figure out how we're going to get to our goal, how we're going to get to our overall. So I kind of start by like looking at my reactants and my products of my overall and trying to find them in my equations I was given. So the first thing that kind of stands out to me is, let's kind of go one by one. I see that this reactant is there. So on the reactant side in a 1 molar ratio, which is exactly what I want. So maybe I don't have to mess with this one. I notice I have some O2 on the reactant side, but not 2 of them yet. But I don't know. I don't think I want to multiply that whole thing by 2 unless I really have to, because I already noticed that I have 1 of these. And so maybe let's not mess with that quite yet. And then I notice my other thing I want is my product right there. But in this reaction, it's on my reactant side. So what I'm going to do is flip that whole thing. So since this is our first one, I'll kind of write it all out for you. I'm going to leave that reaction 1 as it is. So, maybe we have to come back and change it later, but let's just kind of write it out. Sorry. So I have N2 gas, the O2 gas, going to form 2 nitrogen monoxides. Okay, and I already recognized, and this might be a guess and check. Maybe you change one thing and then you have to change more, but let's just try flipping it and see where that will get us. I recognize that I want to flip this because I need that as a product. So flipping it around, instead, now these are my reactants. And now this is my product. And whatever is done to your reaction must be done to your enthalpy. So this first one, we didn't change it. So I'm just going to write the same one we got from earlier. This one we flipped. So I want to make sure that I change the sign of my enthalpy. Okay, so let's see where we're at with this. So let's just try. Let's write our overall, see if it's what we want. And if not, back it up, try again. Keep messing with it. But let's see. Right now, let's see what can cancel out. I see that these two cancel out, and I think that's it. So let's just add these up. We have N2 gas plus 2 O2s goes to form 2 nitrogen monoxides. Or no, nitrogen dioxides. Cool. All right, so double check. Here is the way I have it written right now. That's my overall. And here is my goal. Checks out. It matches. So that means that if I want to get the reaction energy of this, I will add up these two enthalpies. So 180 plus 112 our actual energy for this reaction is the kilojoules per mole. Cool. So maybe try the next one, see if you can do it. I'll walk you through it when you're ready to see that. So first of all, again, I got this from some like random website, and I didn't realize they didn't put the kilojoules in, or per the poem. They're all written just as kilojoules, which is a thing that people do. To be honest, I don't really understand why. I think it's some like mind logic of like how they're representing it. I think it's silly. So I'm going to do per mole just to be consistent for what we've been doing so far. If you see it as just kilojoule in like a problem and they ask for just kilojoules, give them just kilojoules, but that's neither here nor there. Okay, let's solve this guy using Hess's law. So if you see a stack of a bunch of different reactions, it's going to be Hess's law. So let's see if we can figure out how to mess with this guy. Again, since we're just practicing, I'll write them out for you. On like an actual like test, I would probably save myself the time and just make notes up here of like what I'm doing to them. But you know, as you practice, if that's something you prefer to do, go for it. If you're more a visual person and don't see those steps, maybe you want to write it out the way I'm writing it out now. Okay, so let's look in for this. So looking at my first reaction, the first thing I notice, I have a reactant, and over here sorry, I have what I want as my product written as a reactant. Alarm bells, that probably needs to be flipped. And it's nowhere else in the other reactions, so it's not going to come from anywhere else. We definitely need to flip that first one. So I'm going to do that first. So flipping it around, making my products into reactants now. And since I flipped it, my enthalpy for that step is now going to be, it was negative 1,299.5 kilojoules per mole. But because I flipped it, now it is going to be positive. Okay, let's look at our second one. What I'm noticing here is that I have carbon, which is what I want in my overall. It's the only reaction with carbon, so it's the only place I'm going to get carbon from. But in my overall, I have two of them. So I'm noticing I have to do multiplying that whole thing by 2. So let me show what that would look like. So now I have 2 carbons instead, 2 oxygen gas instead, forming 2 CO2s. Okay, so I multiplied that whole thing by 2. I also have to multiply my enthalpy by 2, which would now be 178. No, that's 787 kilojoules per mole. All right, cool. So there's that. And then the third one, I don't really see much about like what I could do with that. So let's see if we even have to change it. So I'm just gonna write it down as is, see where we're at with it. If you don't get your overall, you'll keep messing with it. But I'm just gonna write it down as is. And again, I think it's kind of tedious to write this all out. So especially if you're doing a multiple choice question, I encourage you to come up with a different way of doing it. I tend to just annotate it on my reactions. Didn't do anything to that one, so just using the enthalpy given. All right, so let's check where we're at with this. I have a water and a water. I have 2 CO2s, 2 CO2s. I have 2.5 oxygens, 2.5 oxygens. So my overall is 2C. That's definitely a solid. It's just a poorly written solid, plus my hydrogen gas goes to form my ethine. And it's a gas. Cool. All right. Does that match my goal? Yes, it does. Those are the same, which is how I know I did it right. And that means I just get to add up all these boys. So that means this plus this plus this plus this. And I'm just gonna write that my enthalpy of reaction is equal to 226.7 sig figs, I suppose. 27 kilojoules per mole. All right. And that is that. And we are done with Unit 6. So yeah, a little bit tedious with these last few ones, but hopefully not too challenging. Just kind of take a little bit of practice. And yeah, so let me know if you want any help and good luck.